All right, section 5.8 is called average value. Average value. All right, so an average value, just like if you were finding your average grade in the class, if you wanted to find out your average grade in the class right now and you didn't have Jupyter to look at it, but you had all of your grades, what would you do to find your average value in the class? Add up all the points you've earned, and then what? Divided by all the points that are possible, right? So you're always doing this division by a quantity of what was possible. And this is very, very similar to that. This is the average value on an interval. The interval is from A to B. What you will notice is that it's the same antiderivative notation that we've been doing now for about a week. Integral from A to B of f of x dx. But then you're dividing by the length of the interval. That's the only difference, is this extra tiny little piece of division. That's all. So we just did a problem about laboratory mice, right? So if you wanted to find the average weight of a laboratory mouse in, from a 2-week-old to a 5-week-old mouse, you would simply find the area that we just did the problem for from 2 weeks to 5 weeks, and then you divide by 3 because the difference between 2 and 5 is 3. And that's the only difference at the end, is you would be dividing by the length of the interval that you were looking at. Okay? So we're going to do an example. Did you have more to write? I can go backwards, I'm sorry. Divided by the length of the interval. And then there's 2 ways, of course, I just wrote it. They're not substantially different, but you can use either one you like better. Okay, you guys ready? We good? All right, U.S. factory sales of electronic goods to dealers from 1990 to 2000 can be modeled by the equation S of t equals 0.0388 x cubed and so forth, $billion, x years since 1990. Use a definite integral to approximate the average annual value of U.S. factory sales of electronic goods to dealers from 1990 to 2000. So this says we're going to find the average annual value. It's the average value we're talking about. And we're going to do this from 1990 to 2001. And our values are actually going from years since 1990 in the problem. Okay, does everybody see those pieces of information? All right. So what we want to do, this is the same question over here. I just copied it because I knew I didn't have enough space. So what we want to do is we want to take the interval, or the integral, of our function, which happens to be called S of x dx. And what do we want our a and our b to equal? 0 and 11. Because it says from 1990, and this is years since 1990, so that's 0, and 2001, and that's 11 years since 1990, so that's 11. And then we want to divide this whole thing by 11, because that's the difference between 11 and 0 is 11. And I like to write this at the beginning just so that I can do it at the very end of the problem instead of worrying about a denominator that I'm carrying along. Just write it at the very front. All right, so looking back over here at your equation, I don't have it on my screen, I should have. Actually, let's just write it here below. Let's find the antiderivative of this problem. So, what is the antiderivative of 0.0388 x to the third? What do I do with the constant? I leave it. So it's 0.0388. All right. What am I going to do with x to the third? X to the fourth divided by 4. All right. How about the next part? How about the negative 0.495? I leave it. What do I do with x squared? X cubed divided by 3. The next piece is 5.698x. So what's that one? So there's 5.698, and then I'm supposed to square it because it was power 1 before, and divide by 2. How about 43.6? Right, 43.6x. Plus c is what we normally do, right? I mean, plus the constant. Now, here's the catch. The plus a constant's not actually going to matter because this is finding an average between the two values. So we don't have to worry about the plus the constant on this particular one, okay? So it's not a concern. And it has to do with the fact that we're going to be evaluating this between 0 and 11. So it would actually cancel itself out. So let's take a look. I'm going to move this from this page. Oops, hang on.
Did you say it didn't matter if we put the divided by 4 over all of it?
Correct. It doesn't matter if you put it over all of it, yeah. Okay, so it occurs to me that I haven't actually shown you what to do with the 0 and 11. We talked about it back in 5.2, but we haven't actually seen it used since then. So let me move this over here. Am I off my screen yet? No. Okay. And then I'll show you what we do with it. Okay, so we have this 1 over 11 in front. I'll put it back over here. I'm going to put all this in parentheses. I'm going to show you what we're going to do with the 11 and the 1, or 0. You ready? Okay. You're going to write a line at the end. You're going to put 11 at the top and the 0 at the bottom, just mirroring the 11 at the top here and the 0 at the bottom here.
We don't have to have a plus c in this?
We don't, and I'll explain why after I show you the problem of what we are going to do with it. Yeah. All right, what we're doing is called a definite integral. We have a starting endpoint and we have an ending endpoint, and we're using those endpoints. What are we using them to do? Well, we're using them to evaluate what happens in 11 and what happens in 0. So the way that we do that is we plug the number 11 in. So in this problem, what we're literally going to do is we're going to take the number 11 and we're going to plug it in everywhere we have an x. Okay, all that's in big parentheses. And then we're going to subtract, I'll show you a notation for this in a second, I probably should have shown you that to start with. The same thing with 0 plugged in everywhere.
And all that's going to be in parentheses.
Mm-hmm. You guys like multiplying by 0, right? Okay, so we're subtracting all of this, and then we're doing all of that times the 1 over 11. Okay, so here's the cool thing. What happens when I plug in 0 to this function? It's 0. Polynomials do that because they're all multiplied by 0. So do I really have to figure out I don't really have to plug in 0, right? I mean, like it's just 0. So you can grab your calculator and you can plug in the number 11 to the function. And I will wait till next time to show you a cool calculator trick because I can't show you on my screen today because it's, not working. There is a cool trick. You remember when we did inderiv and we were able to actually let it calculate something for us without having to plug it in by hand? There's a way to do that with antiderivatives as well, so I'll wait till Monday to do that with you, or Tuesday, excuse me. But if you plug in the number 11, what do you get? What number do you get? Got the 1 over 11 in front. I want to know what happens when I plug in 11 into this antiderivative. Anybody have a solution at all?
Just 11.
Yes.
133.804.
Do I have confirmation from anyone that that's what you have as well? What do you have, Lainey?
464.681.
I don't have either of those answers, by the way. Mine's close to Luke's, but it's not quite. What did you get, Kendra? Giving it a try, several people trying. Who has another option for us? Did you go back and look at it again? Lainey and Luke are the ones who gave me answers.
745.643.
You're getting closer to what I had. What do you have, 745 what?
0.643.
And I'm not guaranteeing that the number I have written down is right. I don't know. Maybe I should grab my calculator. I'll check with you.
Do 746.
Ooh, that's what I have.
0.73.
746.732. That is what I have. Wow. Ding, ding, ding. We have a winner. Maybe it is a game show. Okay. All right. Say it a little bit louder. What did you get?
746.732.
Let's keep a couple more decimals just in case because we're going to divide by the 11 here in a second anyway. What do you have? Just give me, let's go with 4 for now.
7317.
7317? Okay. And then from that screen, let's actually hit divide by 11. That's the 1 over 11 in front. That's giving us an average value. What is it?
I did that.
You did? Okay. Oh, you did the divided by 11 part already.
Oh, I
Okay.
got that now.
You got that now.
I
Fantastic.
forgot an 8. I only put one. I only put
0.038. Tiny little number it'll be. Okay, what do we get when you divide by 11? Brock, what did you get when you divided by 11?
67.885.
67.885?
Yes.
Feel good? Okay. All right, so let's talk about a couple things that have happened so far. The first thing that I'd like to talk about is that what we did here is we took a function and we did its integral from a to b, and it became another function, capital F of x, and I put this line at the end where I put a b and an a here, right? This is what we did. And then what we did is we evaluated it at b, and then we subtracted the evaluation at a. That's what we did, okay? Back in section 5.2, I think it was, there's a name for this. It's called a fundamental theorem of calculus. Okay, we're evaluating at the first point, evaluating at the second point, and subtracting. So that's the first thing. I mentioned that it didn't matter if we put a plus c in, and I'd like to show you why. Let's say that we had that's what it would have looked like. I've put the plus c's in everywhere. But what happens to the plus c? It gets subtracted off. It's plus c right here, change colors, and then I've got a plus c right here that is then subtracted. So it just subtracts itself off. It doesn't end up actually affecting anything. That's why it doesn't end up mattering that we had it there. Make sense? Okay, we're not quite done with this problem because this problem had context and we haven't actually written any of the context with it. Agreed? Yeah. All right, so this says that this is, billions of dollars X years since 1990. So we're supposed to be multiplying billions of dollars times the years. Right? $1 billion times years. And there isn't a per that gets canceled out. Agreed? Okay. But take a look at what we're actually doing over here in this definition. This piece right here, from what we just found, gives me billion, in our problem, $1 billion times years. Agreed? But what are we dividing by in our problem? Years. 11 to 0, right? This was in years. So we've got $1 billion times years divided by years. So what happens? Years cancels. So our problem's units at the end are in billion dollars. So the average, what was it? The average electronic sales over this time frame per year, their yearly sales, annual sales is $67.885 billion. Average annual sales. Part B asks us to sketch a graph for this. So go ahead and grab your calculator, put the original equation in, okay? And in your calculator's original equation, I want you to graph this between 0 and 11, because it said between years 0 to 11. So that's what we're going to go with. Not anything you calculated, but the original function that you were given. So you're welcome to do 0 to 11 and then zoom 0. That's zoom fit to get a picture of it. Presumably. I don't think I put mine in right. Let me try that again. Yep. I don't think that was right either. All right. Okay, what does your function look like? Is it going up or down?
Up.
What have I entered wrong into my calculator? I'm missing a variable. That's what's wrong. Okay. It's like it's not matching what's on my screen. That is now. Okay. I also like to make our y minimum 0. If you'll graph that again, hit y minimum 0, and then you'll get a picture that shows the x-axis. So the graph ends up looking something like this. Is that close to what your calculator looks like? And it's going from 0 to 11, so we'll kind of mark that 0 to 11. What I'd like for you to do is to hit y equals. And in y2, I would like for you to put the 66.8 whatever we had. What was it? 885. Just 66.885 in y2, and then hit graph. 66.885 into y2. What was it? Did I say anything wrong? Oh, was it supposed to be 67? Oh, sorry about that. I'll fix it. It probably won't look any different on my screen, but I will fix it. Okay. So it looks something like this. All right, does that look right? Roughly speaking? Here's the cool thing visually, and my graph's not perfect. The one that's on your calculator is a better version to look at to be convinced of what I'm about to tell you. But what this does is it takes this oddly shaped curve and all of the area underneath it, and it repositions it to a rectangle of the same area. This rectangle, I'll shade them in. This piece right here, its area, is the same as the area of this rectangle. Imagine it's Play-Doh and you're squishing it into a different position. The volume of the Play-Doh didn't change, right? But you turned it into a different object. That's what average value is doing. That line that's cutting through the middle is balancing it out in terms of the area. It's likewise balancing out the space. If you imagine this space right here, basically what it's doing is balancing this space. That's what's happening. It's repositioning them so that they're actually filling in the rectangle instead of filling in this odd looking shape. Visually, that's what average value is doing. All right, we have one last example, and it is one where you're going to create an equation. So if you have a calculator, I'd like for you to go ahead and put this data in. Let's do this in years after 1980 so that we're all doing the same thing, all right? So we're going to put in 1982 as what? 2, and 1984 is what? 4. So be careful as you're looking at these because they do not all increase by 1. They do on some of them, and then all of a sudden we jump up to 15 and 20, okay? So our inputs are going to be those. Remember the way that you do that is you hit stat edit, and you're going to put in those values. And as always, you never put the L2 in any differently. You enter it just like it was given. Okay, this problem says, let me read the context. The most expensive rates in dollars per minute for a 2-minute phone call using long-distance carriers are listed in the table below. You guys don't even remember when long distance cost you. You know, your cell phones just call long distance, it's no big deal. That has not always been the case, even on your cell phones actually. But once upon a time you had to pay for it. So if you take a look here, apparently 1992 you paid $1.50 per minute. How expensive would that have been to call home? You probably wouldn't be talking to your parents very much at $1.50 a minute. Maybe that would be happy for you, I don't know. All right, so we're going to find a model, and it doesn't say what the model's supposed to be, correct? So how do we decide that? You got to graph it, right? You've already put the data in. If you clear out your y equals from what we just did it before, and you turn plot 1 back on. So right now you should have nothing in y equals, and plot 1 should be on. And hit zoom 9, that's the stat menu. Taking a look at your scatter plot, what does it look like would be an appropriate model to try? Any guesses? Somebody said something. Exponential looks like a viable option, doesn't it? Yeah, and possibly quadratic if the exponential doesn't fit. But given what the trend is in the data, exponential's end behavior seems more appropriate. Would you agree? I mean, we don't expect the long distance to come back up in terms of the cost. So let's try exponential and see if it's a good fit. So the way we do that is we do stat calc, go down to number 0, that's expreg, and put it into y1. You need to graph it to see if it's going to fit it okay. Mine looks pretty good. Does y'all's look pretty good? Okay. You should now have an equation that you can write down. The equation that we're going to write down, we need a name for it. What do you want to name our equation? How about f of x? We'll be super creative today. F of x. And let's see, our a value I've got is 1.916. Does that look right to you guys? And then it's b to the x. The b value is 0.892 to the x. That's the numerical part of our equation. What is the rest of our model? Okay, good. So here's my rate, dollars per minute. And then what? Yeah, x is the number of years since or after 1980. It says use a definite integral to estimate the average of the most expensive rates from 82 through 1990. Okay, so we're averaging these. So we're going to do our integral from 1982, that's 2, through 1990, so that would be 10, of our function, f of x, and we're going to divide it by or multiply by 1 over what? 8. So I'd like for you to take this equation here and let's find its antiderivative. So what is the antiderivative of 1.916 times 0.892 to the x?
1.96 plus 8.9.
Times,
Or divided.
yeah, 0.8, what was it? 892. Go ahead, Lainey, what did you have next?
9x divided by ln.
Good. Okay, this is the antiderivative. If we were doing a general antiderivative, we'd put plus c on the end. We're not, because we have limits of integration. We have numbers on the top and the bottom. Those numbers, we write the line at the back, and we put the numbers at the end. Oops. 10 and 2. And I need to put a 1 over 8 in the front of this. So I'll wait to do the 1 over 8 in the very end. You could multiply it through if you want to right now. It wouldn't hurt anything. So we're going to have the 1 over 8. And we're going to evaluate this function at 10. So 1.916 times 0.892 to the 10 divided by the natural log of 0.892 minus 1.916 times 0.892 to the 2 divided by the natural log of 0.892. You're going to input those values, you're going to subtract them, and then you're going to multiply by the 1 over 8. We'll do units after that.
Multiply by 8 before we get the answer.
Divide by 8, you mean? Or multiply 1 over 8? Yeah, that would be good. You can get the whole thing if you want to at once. What did you get?
0.999.
Got lots of nines. 0.999.
0977.
Yeah. So if I write down a bunch of decimals, that's 5 decimals, and there we could write more, of course. Let's figure out what the units are. Normally 3 decimals is what we would do, so we would put 0.999. There's something about this one, though, that makes it a little bit different. This is dollars per minute, and then it's times years. Remember, it's multiplication of the input and the output. So dollars per minute times years. And then what do we divide by? Because I've got this 1 over 8 at the front. What is 8? 8's in years. So what happens to the years? Cancels. And you know what? It's the second time we've seen that happen. What do you think that might mean? It happens every time. The output and what you're dividing by, the input value over here and what you're dividing by always cancel. You always end up with the original output of the problem. So this is dollars per minute. So it kind of makes sense to say that it's not really $0.999 per minute, right? $1 per minute is probably a more realistic kind of value to say. Okay, let's just talk through. I won't do it, part C, and that way you guys can finish it up on your own. Well, the only difference on part C is what from part B? The interval. The interval goes from 1982 to 2000 instead of to 1990. So the very beginning part will be 1 over what? 18, because it's 18 years. So our interval looks like this from, that's 2 to 20 dx. Let me just tell you what the answer is so that if you're confirming this later, you have the right thing. This ends up being 64 cents per minute on this particular problem.